Swayam Prabha. Digital India. Educated India.
Lecture of this course, Fundamentals and Application of Dielectric Ceramics. So, we will just briefly recap what we did in the previous lecture. In the previous lecture, we looked at non-stoichiometric oxides primarily. So, we looked at two dominant cases of oxygen deficiency and metal excess, or we looked at oxygen excess and metal deficiency, right. So, the first one can be determined as MO1 minus X, this could be M1 plus XO, this could be MO1 plus X, and this could be M1 minus XO. Okay. So, essentially in the first case you form vacancies of oxygen, and they can be compensated either electronically by forming electrons, or they can be formed by reduction of metal at metal sites. In case of metal axis, you form metal interstitials, which can be again compensated by formation of electrons or reduction of metal site. Generally you do not talk about changes in the cation valences, so generally it is metal which reduces, oxidizes. And oxygen excess can be accommodated by formation of oxygen interstitials, which can be compensated by formation of either holes or metal oxidation. Okay. And metal deficiency can be accommodated by formation of metal vacancies, which are compensated by formation of holes or again oxidation of metal ions. And there are various oxides which follow these things, and as a homework I requested you to do exercises on MO, M2O, MO2, M2O3 and so on and so forth. So, this will allow you to do exercise, this will allow you to understand and just ensure that you have site balance, you have mass balance and you have charge balance. You have to preserve these three to write correct defect reactions. Now, let us look at another case which happens in oxides, which contributes to defect chemistry in a very significant way, that is effect of impurities. And the reason for that is because nothing is pure in nature. Okay. Thermodynamics itself prefers the impurities, and as a result there are always impurities present. So, if you have oxide MO, you might have a impurity which is M prime 2O. M prime is probably not a good idea. Let us say I have an impurity which is A2O. Okay. I can have an impurity which is AO, I can have an impurity which is A2O3 in very small amounts, and these impurities could be either substitutional or they could be interstitial. Okay. So, depending upon how they are present, what kind of valences of these cations are, they affect the defect chemistry of the parent material. So, let us say the case 1, in which the parent oxide is, so parent oxide is MO and foreign oxide is or you can say impurity oxide is A2O3. Okay. So, what are the possible scenarios? You can have various possible scenarios. So, the first possibility is that this impurity atom, which is A, occupies M sites in MO. Okay. Now, if that happens, let us say A2O3 goes to MO. Okay. So, which means 2A go to M site. Okay. What must happen? MO host lattice has a site ratio of 1:1, right. This is the host site ratio, and impurities cannot disturb that. So, when 2 A's go to M site, 2 oxygens go to oxygen site. So, site ratio is maintained, which means the extra oxygen has to go out. Now, this A is 3 plus, M is 2 plus, which means it will carry one positive charge. How is this going to be accommodated? By creation of a electron. So, this is going to give rise to 2 electrons. So, this is electronic compensation, which means impurity of A2O3 type will cause a N type behavior in. So, just like example could be, if you have Al2O3 which let us say goes into ZNO, what will happen? This is 2 Al going to zinc site. So, this is example, plus 2 oxygen going to oxygen sites, and another oxygen goes out, and then 2 electrons. So, basically doping of aluminum into zinc oxide has created electrons. So, aluminum doped zinc oxide is an N type semiconductor, and that is what it is. The aluminum doping of zinc oxide makes it a N type conductor. This is something that you do purposefully, but if you do not do purposefully, this might happen inadvertently if you have impurities present. What is the other possibility? So, this is the first possibility. What is the other possibility? The other possibility is A2O3 is in MO, 2AM plus let us say all the 3 oxygens go to oxygen site. Now, the site balance is disturbed because you have created 3 oxygen sites, but you have only 2 metal sites, which means one of the metal sites will be vacant. So, this is ionic compensation. You will create metal vacancy. So, this is electronic compensation, this is ionic compensation. Again, the charge balance, the mass balance, the site balance has to be maintained. Site balance by creating a metal vacancy is 1:1. If you did not have that, then you will have site imbalance. In the previous case, only 2 oxygens went to oxygen sites, one of the oxygen went out. So, again the site balance was maintained, and site balance is that of the host lattice, not of the foreign lattice. Okay, is that of the host lattice, because the host lattice is the one which is accommodating the impurity, not the other way around. If you have other way around, you will have to do it other way around. Okay. So, this is one possibility. Now, another thing which these impurities are used for is, suppose now imagine if the host oxide was, so you can use it positively. Let us say if the host oxide was oxygen deficient, that is, it contains VO, that is, it contains VO to begin with. So, you want to now get rid of oxygen vacancies. What do you do then? You have oxygen vacancies to present in the system, which means if I am doping with the oxide with higher valence, which means I am bringing in extra oxygen to the system. So, if I am bringing in A2O3 and this goes to MO, then basically 2 A's go to M site, 2 O's go to oxygen site to maintain the site stoichiometry, but you have one oxygen vacant site. This oxygen vacant site can be filled by this again oxygen site. So, now you do not disturb the site balance. You had one site here, you have filled that site with extra oxygen, and two other sites which were created, they are balancing each other. So, this is basically another way. So, you can write this as 2. So, this can be this is positively charged, this is again positively charged. So, you have positive charges balancing each other, the sides balancing each other, and the, so essentially you can write this as 2 Am dot plus 3 Oo. Side balance is there because you have two metal sites, and one of the oxygen sites is compensated by this site, and for the two metal sites you have two metal sites. Okay. So, side balance, mass balance, and charge balance is there. All right. So, this is how you can use it to your advantage. If you want to reduce the oxygen vacancy concentration in an oxide, you can dope it with a oxide with higher valence. Okay. So, you can dope, so one example could be, let us say we have BaTiO3 minus delta, it has oxygen vacancies. So, if I dope it with, let us say Nb2O5, niobium goes to titanium site. Okay. So, basically what is it? It is BaO.TiO2, barium titanate, right. So, if you put niobium in this Nb2O5, you have vacancies of oxygen in the system. So, 2 niobiums go to titanium site plus 5 oxygens go to oxygen site. So, this niobium will be positively charged. So, out of these 4 are related to titanium. So, because Ti is to O is 1:2, right. Okay. So, out of these 5, so you can write this 4Oo plus Oo. So, 4, so this is side balance 1:2, and this is compensated by this extra one. So, this is how barium titanate is made more resistant. Okay. So, barium titanate may have electronic defects, it has oxygen vacancies. So, how do you eliminate oxygen vacancies? You bring in extra oxygen into the system by doping it with a oxide of higher valence. This is called as compositional engineering of oxides. So, not only impurities can give you defects, but impurities can also be used to compensate the defects which exist from earlier. Okay. Alternatively, if you have, let us say, holes in the system or electrons in the system, in this case if you had holes in the system, if the system had holes, then you again dope it with A2O3, then 2A go to M site plus 2O go to O site, and this becomes half O2. So, you can reduce the whole concentration by doping it with a higher valence oxide. So, basically you can reduce the amount of defects if your oxide was already defective. Okay. So, appropriately you can choose, for MO you will choose M2O3, but for M2O you can choose MO. Okay. Alternatively, if you wanted to control the metal vacancies, then you will have to go for lower valence stuff. So, that is how you do. So, what I would like you to do is that as a homework you should do write various defect reactions for dissolution of A2O in BO. Okay. Right, do the other way around, and then what happens if BO is already defective. Consider both oxygen and metal deficiency. Okay. So, do this as a homework. This will be useful for you to understand the cases that we have done just now, all right. Now, the next thing is to look at, so what we have looked at until now is we have looked at the stoichiometric defects which do not change the stoichiometry of the oxide, like Frankel defect, Schottky defects, and then we looked at the cases of non-stoichiometric oxides where you have oxygen vacancy, you have oxygen excess or metal excess, or oxygen deficiency or metal deficiency, and depending upon ionic or electronic compensation you will form appropriate defects. The most important thing to consider is site balance, mass balance and charge balance. If you get it right, you will get the defect reactions right. If you do not get it right, then you will not get the defect reactions right. So, but they are very simple to understand. You just have to match there should be no extra sites in the system, there should be no extra masses in the system, there should be no extra charges. Solid eventually has to be charge neutral whatever you do. Okay. Now, let us say, so some of these materials also contain, now we know from elementary thermodynamics that things like vacancies in metals, they are stoichiometric, they are defects which exist under equilibrium. Okay. So, similarly in these oxides, these defects depending upon the nature of depending upon the energy of these defects, the defects formation energy, whether Schottky defects or Frankel defects or anti-Frankel defects, these defects will exist thermodynamically. So, we would like to calculate the concentration of intrinsic defects in a given system. So, let us say we consider Frankel defect. So, let us say we consider a halide Mx, and in that the reaction can be written as Mm plus Xx, this is written as Vm plus Mi, and X remains at X site. So, this is a Frankel defect. You do not change the stoichiometry remains same, the site balance same, the metal, there is one metal site, there is one anion site, and interstitial site is a site anyway, it is at the interstitial site. So, you do not create any extra sites in the system. So, what you are creating is a pair of metal interstitial and metal vacancy. So, free energy change in free energy, that is delta G upon formation of, let us say, small n number of Frankel defect pairs, because they have to form in the pair. So, let us say we form n pair, and what is the delta G that happens. So, and we say that delta Gf is the energy of expense for one pair. Okay. So, G minus G naught, which is delta G, is equal to N delta Gf, which is the enthalpy term, minus the T delta Sc. So, this is the change in enthalpy, which is nothing but number of defect pairs multiplied by the energy that you need to create one pair. Okay. That is delta Gf. You can write it as delta Hf if you want, and but the moment you create these defects, there will also be a change in the entropy, and most importantly the configurational entropy, because earlier you were starting a system like this. So, you had a system which was like this. So, in a perfect material system would be like this, right. The imperfect would be you create this as a vacant site, and this will go somewhere, let us say here, the interstitial site. So, this will be Mi, this will be Vm, but now where can you put it? The configuration has changed, it does not need to be here, it can be somewhere else. So, there are various possible configurations, as a result your configuration entropy will change. So, delta SC is nothing but change in the basically it represents the number of ways in which you can arrange these species entropy, and this is actually positive in nature. Okay. So, basically the equilibrium concentration of defects, this small n, will be, so there will be certain finite value of n only if the free energy is negative at that point. There has to be free energy minimization, which means we would like to minimize this free energy with respect to n, okay, to find out the value of n at which free energy is minimum. So, we need to do certain things. So, let us say you have number of Frankel pairs is n, and so n number of Frankel pairs, they lead to basically ni number of formation of interstitials, right, and n is nothing but equal to ni, okay, n number of pairs, and each pair will contain one interstitial and one vacancy, and similarly it will also be equal to nv, which is number of vacancies, right. So, we write this n is equal to ni into nv, assuming that capital N is the number of lattice sites, total number of lattice sites. Okay. So, number of ways to arrange the vacancies is we can write, let us say this is equal to Wv. So, Wv will be equal to factorial n divided by factorial small n into factorial of capital N minus small n v, which is equal to n small n. Okay. We have just similarly the number of ways in which interstitials can be arranged. That is Wi, and this is equal to again factorial n divided by ni factorial into, and since ni is equal to nv, and so total number of possibilities is W is equal to Wi into Wv, all right. So, you just basically multiply this, and you can do the maths by yourself by applying Stirling approximation and so on and so forth. So, if you do the and delta SC is nothing but k ln W, right, and you replace this W in this form, what you will get is essentially delta SC will equal to k of ln factorial n divided by n minus ni factorial into ni factorial into capital N factorial into nv factorial. And this is how, and if you, and since we know that nv is equal to ni, and we apply, so first condition is nv is equal to ni, then second approximation is Stirling approximation for a large n, that is ln of n factorial is equal to n ln minus n. Okay. For a large value of, for a large numbers, we make this approximation. If you apply this, then what we get is, so you can do the maths yourself, we need to delta SC is equal to 2 small k is the Boltzmann constant, n ln n minus n minus n ln minus small n ln n, and hence the total energy change is delta G is now equal to n delta Gf minus of 2 kT n ln n minus capital N minus small n ln. Okay. And so we can write this as, let us say we write this as can just do some more changes here, delta n Gf minus 2 kT. So just do some more approximations, you will get something like that. Okay, you will get these expressions. Now what you have to do is that if vacancies were stable defects, then at certain concentration the free energy would be minimum. That means at a stable vacancy concentration or defect concentration, delta G should be minimum. So which means del of delta G divided by del of n must be equal to 0. Okay, we must get some solution at that point, and we also assume capital N minus small n is almost equal to n, because small n is very small as compared to its of the order of ppm or even lower. So if we make that approximation, then we can work out this as small n divided by capital N, which is equal to exponential of minus delta Gf divided by 2 kT. So this is what basically it works out to, that there is a equilibrium vacancy concentration which is equal to, which is proportional to delta Gf exponential of minus delta Gf. So basically what it says is that 1 defects are thermodynamically stable at T greater than 0 Kelvin. So as long as temperature is more than 0 Kelvin, they are stable. Okay. 2, as defect formation energy goes up, energy increases, the small n will decrease, which means stronger the defect the more the energy you require to form the defects, the lower the number is, which makes sense. And third is, as temperature increases, n increases, and this happens in an exponential manner. You can further simplify this, you can write this delta Gf as delta Hf minus T delta Sv, where delta Hf is the enthalpy of formation of defects and delta Sv is nothing but vibrational entropy change, but it is approximated as delta Gf to be equal to delta Hf, because the vibrational entropy change is very small. So this is very small, and hence you approximate this as n by n to be equal to exponential of minus delta Hf divided by kT, where Hf is basically the enthalpy of formation of defects. Okay. Similarly, for Schottky defects, you can write this similar expression, you will, so this is 2 kT, sorry, not 1 kT, 2 kT. Against in metals you have 1 kT, and in stoichiometric oxides you have 2 kT. Okay. Similarly, you can get for Schottky defects also, which I am sure you can work out easily. So we will stop here. What we have done is basically we have looked at the cases where you can form defects upon dissolving impurity, or you can put an impurity to change its characteristics, and we have also seen how Schottky and Frenkel defects are stable defects thermodynamically, and we can calculate their concentration in a simple manner. So we will stop here. We will further proceed on this in the next class. Thank you.